So the idea of today's lecture is to complete the exercise that we started last time, for which we, if you remember, we were able to derive the shape matrices for this flexible beam element going from A to B in this slider crank mechanism. So this is just a slide, encompassing and summing up all the hypotheses that we have done with all the data. And so this time we will proceed to further derive the mass matrix for this body, the stiffness matrix, the external forces, and the constraints. So all over the different points that we have theoretically derived so far. So this is just a practical application to see, with hands-on how to actually deal with this. So I'm not sure. I think this was 2. There we go. So I will call this mass matrix. So as we know, the mass matrix was for this body in general, for all the bodies that we have, can be written in terms of submatrices, like so. Again, for the sake of clarity, I am omitting the I superscript, because we know what kind of body we are dealing with. Again, it's the shaft AB. Okay, so, and here it's symmetric, of course. And the idea is to go and check and see how to derive these quantities. So let's see. We start 2.1 with the submatrix MRR. Okay, and okay, I'm not spending too much time on this, because this, as you know, is just in our 2D case, this. It's a diagonal matrix, where M is the mass. The total mass of the body. And it's constant. Okay, so the idea here is also going to see what are the features of this submatrix in terms of relationship with respect to the rigid and the flexible coordinates. Okay, so in this case, you can say that this is a constant. This is a constant matrix, and not just in this case. Typically, this is the case for most of applications, unless, for example, we are dealing with a body which loses or increases its mass during its operation. But unless we are dealing with these somehow extreme cases, this is what we have typically, a constant matrix. All right, then let's go a little bit deeper, and let's go check this submatrix MR theta. So MR theta, we can write, as you know, as the integral of the density times the matrix B that we are seeing, integrated all over the volume of our body. Now, for the 2D case at end, so 2D case, this B can be written, if you go and check the definition of the matrix B, which is the derivative with respect to the theta, as A theta, which is, again, the derivative of the rotational matrix A, times the vector R over bar. And so for this reason, this can be written like so. The integral of v times rho times r over bar in the v pre-multiplied by the matrix A theta, because again A theta only depends on the rotation parameters, the orientational parameters. So it does not depend on space, and that's why we can bring it out from the integration sign. Now, this, if you remember, how we can write R can be written as follows: A theta multiplied by the integral over the volume of rho R0 over bar the V plus the integral of rho times what? Times psi dV in the volume. So this is the matrix. Okay, let's say like this: psi q con f in the V. Okay, so I'm just unpacking R over bar. Of course, again, QF does not depend on time, so we can bring it out again from the integration sign. So this can be written as A times, so the integral over V of rho R0 over bar in the V plus the integral, let's do like this, plus the integral over V of rho psi dV multiplied by QF, all being multiplied by A. No? Now, maybe you're able to recognize two of the inertia shape integrals that we have already introduced, no? The one inside the integral signs. Okay. So we can write the following. We have that, if you remember correctly, R over bar R0, well, let's put it like this, was by definition this. While S over bar psi was by definition the integral of rho psi in the V. Okay, but now we have R0, of course, but we also have psi, because psi is the shape, the inertia shape matrix that we have already defined. We have already estimated in the previous lecture. So this can be written as follows: rho, which is, let's say, the density, A, which is the section, the constant section of our beam. This can be written as a linear integral instead of a volume integral, so from 0 to L, which is the span of the beam, times what? 0, because it's a 1D vector. Remember that R0 over bar, we are in the local frame, so in the local frame, the beam is a 1D element, no? So this is R0 over bar scalar. It should be 1, as we meant. But for the sake of simplicity, we omitted this. All of this being multiplied by the R0 over bar. Now, this amounts to what? Well, we can, again, basically normalize everything. So we have, if you want, and this is m, of course. And this is the integral from 0 to 1 of what? Of xi, that we have already introduced, times the xi. And this amounts to m times L divided by 2, 0. Okay. So this is the first inertial shape integral. And then here instead we have the following. We have rho, A, again, the integral from 0 to L of psi dr0. Again, in this case, we can pass to the non-dimensional coordinates. So this is m, again. The integral over from 0 to 1, in this case, of psi index c. And if you remember the expression of psi, which is a 2 times 3 matrix, this became, oops, m divided by 12 of 0, 6, 0, L, 0, minus L. So it follows that when I apply the second inertial shape integral to my QF, this becomes, if you want I can write it again, but it's really trivial. So we have 0, 6, 0, L, 0 minus L times the deformation coordinates, the elastic coordinates after the imposition of the reference coordinates, of the reference condition, sorry. So we have QF3, QF4, and QF6, because if you remember, the remaining elastic coordinates were basically eliminated in order to remove rigid motion of the beam. And so this, quite straightforwardly, becomes 6QF4 times L QF3 minus, sorry, QF6. Okay, so this is the second part. And this means that eventually my M R theta submatrix becomes as follows, which okay, and this we have everything to estimate this quantity. And so we can write it here. Minus 6 L plus QF4 times the sinus of theta minus L times QF3 minus QF6 times cosinus of theta. Oops. Oop. Let's write it. So this is the first row, and the second row is quite similar. It's L plus QF4 cosinus of theta minus L times QF3 minus QF6 sinus of theta. And as you can see, here we have a linear dependence in the QF, so in the elastic coordinates, and a nonlinear dependence with respect to the rotation coordinates. So let's write it down. So linear in the QF, sorry, let's write it here like so. So while it's non-linear, okay, so you see, this is the perfect example of a coupling between the elastic and the rigid coordinates within the mass matrix. Again, from this definition here, you can see two things that we have already ascertained. That's to say, if you choose the origin, the center of mass, of the body as the origin of the local coordinate, this vanishes. Okay, and of course, if the body was not elastic, also the second term will vanish. And as we have already seen for the case of rigid bodies, this term would vanish if you every time that you choose the center of mass as origin of the local frame. Okay, but if this is not the case, you have all a non-zero matrix. Okay. Again, you see here what is the point of calculating the inertia shape integrals. What do we actually put a lot of effort in estimating these quantities here? For example, here in this case, we have this and this. Because if you have to re-update your mass matrix, okay, within your simulation, in theory you would require to estimate every time this mass matrix, submass matrix MR theta, which is computationally intensive. But if you define the inertia shape integrals like S, R, 0, and S, psi, you estimate it only once, okay, and then depending on the new value of the, for example, in this case, elastic coordinates, you straightforward do a multiplication, and you have already the mass matrix. Okay, that's why even in codes, even in Adams, you have the definition of these inertia shape integrals, because they allow the estimation of the mass matrix to be so much faster. Okay. Okay. Next. We have 2.3, I guess. MRF. Okay. MRF, again, by definition, is A times S psi. See, this is just a multiplication. And this is straightforward again. Oops. Sorry, I think that I missed something here. I think that I missed, sorry, M over 12. I missed it. Times M over 12, multiplying 0, 6, 0, L, 0, minus L. And this is very easy. Okay, and in this case, again, let's make the check that you have a nonlinear dependent with respect to the rotational coordinates. Okay. Now, if we proceed, if we move forward, you have the m theta coordinate. Now, if you remember, this was defined as the integral over the domain of the matrix B transposed over B, which in the 2D case can be written, as we have seen, as R transposed A theta transposed 1 over A theta from the previous definition of B. Now, since A, if you remember, was an orthogonal matrix, A theta as well is an orthogonal matrix. So the product, the result of this, basically, is what? Is the identity matrix. Of course, here we have, and so eventually we have this. And this, if we again unpack R over bar, can be written as the sum of 3 terms, basically. So we have rho R0 over bar transposed applied over R0 plus 2 times the same integral, but this time like this, and then eventually okay. Now we call this m theta r. This we call it m theta rf, and this m theta f. As you can see, they are all scalars here. This is a sum of three scalar quantities. In fact, here we can also, this is a matrix, but eventually it's a matrix with one element, so it's a scalar. Okay. So let's estimate these quantities. Well, m theta r. Again, we can go linear. This is quite trivial to resolve. Okay, so this is the first scalar. Then you have and this can be written like so. I see there is a mistake here. 0 to 1. So here you can call it basically L times C. R0 is L times C. On the other hand, here you have 0. And then you have the what? The shape matrix 0, C, 0. Here you have, so let's write it like this. C minus 2 C squared to the third, and you have 0. And then you have L for the sake of clarity, these are the columns. And then you have to multiply it by QF. Okay, so this is QF3, QF4, QF6. All be integrated in index C. Okay? Because again, so you have, as you can see here, in the previous slide, you have R0 transpose applied over U. And U, if you remember, is the combination of the shape matrix times the deformation coordinate. No. Yeah, let's do it like so. Okay. Okay. And this, if you do C squared QF4 C okay. And sorry, yeah, let's do like this. It's 1/3. Okay. And then eventually we have m theta ff, and this is again rho al, inter from 0 to 1, QF3, QF4. Okay, let's write it directly like so. So F transposed apply over Psi, transposed apply over Psi, applied over QF. And this amounts to m multiplying L squared QF3 squared plus 1/3 QF4 squared plus L squared over 105 QF6 squared minus L squared over 70 QF3 times QF6. Okay? So you see here, you have a quite nonlinear term. Huh? So that if you sum, so you have m theta theta equal to m theta theta rr plus 2 times m theta theta rf plus m theta theta ff, you get the following. M multiplying s squared over 3 plus 2/3 LQF4 plus s squared over 5 QF3 squared plus 1/3 QF4 squared plus L squared over 105 QF6 squared minus S squared over 70 QF3 times QF6. And as you can see here, it's highly nonlinear in the QF. Okay. Then we have the last two. So if I remember correctly, here we are at 4. So this is 2.5. Then we have m theta f. M theta f was again the integral of b transposed over a applied over psi. Again, for the two decays at end, this can be written as r transpose applied over a transpose on a applied over psi. And this amplifies substantially the computation because we have r transpose a theta transpose applied over a becomes the following matrix. It's a 2 by 2 matrix: 0, 1, minus 1, 0. Psi in the V. Now, basically following the previous calculation and substituting what we have seen, above all in R, here we know how to use the inertia shape integrals. We get again the following quantity. ML over 30 L plus QF4, and this is the first column. Then we have ML over 60 multiplying 3 QF6 minus 2 QF3, and this is the second column. Then we have minus ML over 20 multiplying L plus QF4. And again, here you have a linear on QF. The last term is the one associated to deformation. So we have MFF. MFF that we have seen could be defined as rho psi transposed applied over psi. If you do calculation, you got something very simple. Oops. Like so. And of course, this is symmetric. Okay, as you can see, and as we have already anticipated in the theory, this is a constant matrix. Okay. So you see, the calculation of the mass matrix is not trivial also for the very simple case at hand, only for a 2D beam. So imagine a multi-body system with all different, again, corpses, with everyone being associated to a mass matrix, and then you have to calculate all of this. And this is only one part of the, again, of the game, because there are other quantities that you have to estimate, and we will see right now. I'm talking about stiffness matrix. Unless there are questions so far. Okay. So for the estimation of the stiffness matrix, we can start from the definition of the elastic of the strain energy expression. So you have the strain energy can be defined as follows. This is one of the expressions that you have seen so many times. So you have the Young modulus E, the inertia tensor I, inertia moment, in this case. You have the displacement being derived 2 times displacement in the transverse direction squared, plus EA. So A is the cross-section of the beam, and then you have U1 derived only 1 time, so prime, again squared. All of these being integrated all over the beam. So this is quite straightforward, no? So the first term is associated to what? Anyone has an idea? So these are two terms, no? In the elastic energy. The first one is associated to what? Bending. And the second one? So axial deformation. So our beam, and this is because of the physics that we have defined for the beam. No, we have defined a 1D Euler beam. So a 1D Euler beam has the possibility to bend according to to this law, and to extend or compress according to this energy AI. AI is the axial modulus. So with this definition, if we basically rewrite this in a matrix form, this can be written as follows. It's a quadratic form, no? Being an energy, it's a quadratic form. We know it already very well. So we can write it like so. So U1 prime, U2 double prime, applied over the matrix EI, sorry, 0, 0, EI. Multiplied again, U1 prime, U2 double prime, in the R0 over bar, no? I've written just the same things, but in a matrix form. So why did I do that? Because now I know how to express U1 and U2 prime and double prime, no? We have the following. So we have that. So U1 prime is the partial derivative. Well, yeah, okay, partial derivative, because this can also be a function of time. So you have the derivative of what? So if you remember, okay, let's write it extensively. So this is the Psi1, where Psi1 is the first row, not column, row, okay, of the shape matrix, applied over QF. So just to be clear, this is the first row of C. Okay, meaning that we can write like so. Zero. Here we have Xi, so it's R0 over L, and then you have 0. Multiplying QF. And QF is QF3, QF4, and QF6. This is so ugly. If you derive this, you eventually get the following. QF4 over L. No? The same thing goes for U2 double prime. So U2 double prime is second order derivative of what? In this case, we have C2 QF. Okay, this is very long to write, but okay, let's write it nonetheless. So you have R0 minus 2 times R0 squared over L plus R0 to the third over L, and this is the first element. Then if you remember, you have a 0, and then you have, again, between brackets, R0 to the third over bar over L squared minus R0 to the second over L. All of this, again, being multiplied by F3, F4, F6. Okay. And if you do this, you get the following quantity. You have minus 4 over L plus 6 R0 over L squared multiplied by Q4, Q3, sorry, plus 6 R0 over L squared minus 2 over L divided by Q6. Okay. With this in mind, you have eventually the tower strain energy U can be written as follows: 1 over 2. If you do the integral, etc., I will spare you all this. But you can check the algebra by yourself if you want. Multiplying, you know what, let's write it in the new slide. It's the same, I'm just writing it here. Got this, multiplying a matrix, and if you do the calculation, eventually comes out to be the following. Yeah. Okay, so as anticipated, this is a quadratic form. Now, we saw that the elastic energy, elastic potential energy, or the strain energy as you want, could be written as follows: QFT, K KFF times QF. So this basically gives us the stiffness matrix. There are also checks that you can do while you calculate these quantities to see if what you get is actually makes sense or not. For example, look at this expression. Where is it? It is. So look at this expression here of the strain energy. You see, you have this term here, which is associated to which coordinate, to which elastic coordinate, to Q4, and Q4 as well here, right? But what was Q4, QF4? Did you remember? So let's go see if this makes sense. Q4 was, oops, okay. We've been writing a lot. Okay, this will take some time. Q4, if you remember, you see, is the only elastic coordinate which has been left associated to the axial deformation. So that term, EA divided by L, being multiplied to QF4 makes sense because that is the axial rigidity, okay? And this is the only, axial deformation coordinate which has been left. So it makes sense, okay, this coupling. So these are all, checks that you can make to see, okay, but okay, what do I get here? Is this actually correct or not? At least from a conceptual point of view. And the same goes for the other two. For the other two coordinates, Q3 and Q6, which were transverse displacement coordinates, and which were associated instead to the bending, rigidity. Okay. Of course, you can also, so this is the stiffness matrix, the structural stiffness matrix. So the stiffness matrix, it's actually quite easy. So you can write, we have already seen this, U as 1 over 2 of QF transposed applied over KFF applied over QF. But this is exactly as writing 1 over 2 Q transpose applied over K applied over Q, with Q being written as follows: QR, reference coordinates, basically dr, the position of the center of mass, or at least the position of the origin of the log of frame and the rotational coordinates, and then the elastic coordinates. So again, QR is like this, no? And K becomes as follows: 0, 0, 0, Because here in this writing, you should imagine here having r theta, sorry, only one, and then here you should have f, no? B multiplied and pre-multiplied. Okay, is this clear? Okay. And this is not anymore the structural stiffness matrix, but this is the stiffness matrix. Because you remember that the structural stiffness matrix, KFF, is definite positive. Okay? It's never singular. While, of course, as you can see, this one is always singular, because it encompasses the rigid motions, both in translation and rotation. Okay. So this basically completes the estimation of the stiffness matrix. We have two additional quantities that we have to define to close the problem, and they were the external forces and the boundary conditions. Okay, so let's derive the external forces and the boundary condition for this flexible body, for the beam AB of our multi-body system. Let's go to another page. So this is one. I think we are up to 4 now. This, just to keep consistency with the numbering. I think we were up to 3. Yeah, so now we are at 4. Okay. So 4. External forces. So what is the only external force which comes to play here in our exercise? Is the weight, it's gravity. Apart from contact forces, but here we are dealing with, as usual, we make the hypothesis of a constraint of workless contact forces. So our vector of external forces can be written as follows. Okay. So we have a force equal to minus mg, where m is the mass of the body, applied in direction 2, so transverse, in the opposite, in the negative sense, the negative verse. Now, we have that, if you remember, the virtual work of external forces could be written as follows. Where Pg is the position in the global coordinate system of the center of mass of our body. Okay. Okay, let's elaborate a little bit on this Pg. Again, this is with no surprise R plus A, as usual, R over bar of point G. And again, G is R0 G plus the component due to deformation. Okay, so R0 G, can you guess what it is? So R0 G is the position with respect to the local frame of the center of mass of my body. If you go check, I'm not sure if you have it here, let's see. Just a second, because going back every time to the first page is quite uncomfortable. So let's see if I have an image here. Probably so. Okay, yeah, there you go. So you see, the local frame for the body number 3, which is this one, just for the sake of clarity, lies in point A. So what are the coordinates of point G? Imagining, of course, again, that the body has a constant cross-section, is homogeneous, so constant density. Is in the middle, no? So here I should have what? R divided by 2 and 0. Okay? While on the other hand, UG is what? Is the shape matrix estimated at Xi equal to what? 0.5, I would say, no? Times QF. So if you do this, you have that our PG, or actually let's say delta PG, is equal to what? To delta R plus delta A applied over RG plus A applied over delta RG over bar and this can be again written for the sake of simplicity given to our 2D case as A delta multiplied by R over bar G times delta theta plus A, let's actually write it clearly, plus A C calculated at C equal to 0.5 times delta QF. And this can be again written in terms of a matrix multiplication as I, the identity matrix, A theta, RG, okay, and then you have A, C, X equals 0.5, multiplying delta R, delta theta, and delta Q con F. Okay. And therefore, our virtual work, if you remember, can be written as zero minus mg times what we have written here. Okay. So we have again okay. In fact, if you check the dimension of this, this is what? 1 row times 2 columns. This is, okay, in the 2D case, R is a two-row vector. Theta is a scalar. QF, we have seen, is 3, because it's QF3, QF4, and QF6. Okay, so this is a 6 times 1. And this is, in fact, a 2 times 6 matrix. So that eventually you get what? A scalar. And it's true. This is how it should be, because we are looking for a virtual work, so a scalar. But why am I doing this? Because this, we know that the virtual work can be written as follows, as the generalized external force vector Q E R transposed applied over delta R plus Q E theta transposed applied over delta theta plus, well, in fact, this is a, okay, I can still retain the vector, but I know it's a scalar, in fact. Plus QE F transposed applied over the QF but here now we can identify these Q's, which are the generalized external force vectors, the Lagrangian force vector, which are what we are actually seeing in our formulation. So let's see. QER transposed is therefore 0 minus mg applied over I. And this is, of course, 0 minus mg. Okay. It makes no surprise that the generalized external force vector has exactly the same shape of the weight vector. Why? Because it applies directly on U2. So it basically, sorry, not on U2 or R2. So it basically it also associated to a work associated to the vertical translation of the body. Again, remember that this is associated to the vector R1, R2. That's why it has this form. Then you have Q, E, theta well, let's see how it amounts to. So again, it's 0 minus mg from the previous expression times what? Times a theta rg. Rg we have already defined, huh? If you remember. Rg is this one. R0g plus ug. So we can estimate this quantity. And it's the following. Very easy. Okay. And if you do this matrix multiplication, you get eventually this. Sorry, I got confused with this plus. And in fact, it's a scalar, as expected, because it is associated to only one variable, no? In the rotational coordinates, which is theta. So we can actually also remove this. Okay. And then there is the last one. And this is, again, 0 minus mg divided over A, and on psi at xi equal to 0.5. Just a second. Here I made a mistake. Here it's, of course, this is the derivative, no? So this should be minus sinus of theta minus cosinus. The rest is correct. I'm just because it's the derivative here, you see. And so this is 0 minus mg applied to, this time, yes, cosinus of theta minus sinus of theta, sinus of theta, cosinus of theta. applied over 0, 0.5, 0, 0.125L, 0, minus 0.125L. And this is eventually the following matrix. mg times minus 0.125 L cosinus of theta minus 0.5 sinus of theta 0.125 L cosinus of theta. Now it's a 1 times 3 matrix. Okay, so these are the 3 external forces, generalized external forces. No? Again, what are our coordinates? Where we have, in general, no? We have the R, translation, and the external coordinate, the external force associated to translation is this one. So this is the external force which basically is responsible for the creation of work for translation. This is the external force associated to rotation. So when you rotate the body, this is the force that is exerted over the rotation. And eventually this is the force, the generalized force, which is associated to deformation. So it's the force that is associated to the creation of elastic energy, in this case to work, associated to imposition of weight. Okay, so when you impose the weight over your body, over your link AB, the force which will try to move it, to make it translate, is this one. The force which will try to rotate it along theta is this one. The force which will try to bend it and elongate it is this. Okay? So you have decomposed it. So these are called generalized external forces. And we have now treated them and explicitated them, in practice. The last part, and it's very simple, and then we are done, is the part associated to external, the imposition of constraints. So again, let's try to recall our image for the sake of clarity. We have to impose 2 boundary conditions here, at A and at point B. We have 2 hinges. How do we enforce these constraints? And in fact, you will see that this is very similar to what you do in atoms. You actually, when you build your model, and you, for example, you impose a revolute joint in your satellite, you do this. You exactly do this. So we have point A we have a hinge, right? So we have to impose that the position at point A with respect to the body number 3, which can write as follows. Is equal to the same quantity expressed with respect to body 2. If you remember, this is 1, 2, 3, and 4. Huh? So now for the body number 3, we have omitted the superscript, so I will not write it. I will stay consistent with our notation. But for body number 2, I will write 2, just for the sake of clarity. So these are 2 plus A2 and R, A, expressed with respect to the local frame of body 2. Okay. But what is the quantity here? So what is the position of point A in the local frame of body 3? Well, as you see, the local frame in body 3 is exactly located at point A, so this is 0. Right? So our condition is very simply R and of course all this second term will be expressed in terms of the rigid coordinates with which I describe the dynamics of body 2. Because as you remember, body 2 is rigid. Okay, so this will be expressed okay. So I will have the expression of this second term and the equation coming from the same analysis but done on body 2, of course simplified by the fact that body 2 is rigid. Okay, then we have point B. In point B, again, we have a hinge. No? Well, then we have to write, as we have done here, oops, that the position of point B in time is equal to R plus A R B must be equal to, in this case, R4 plus A4 RB4. But again, you see, the local frame in the fourth body is exactly centered in B. So this is 0 again. No? So in this case, let's write, just for the sake of completion, we have RB, which is again R0 B plus U, sorry, C estimated in this case at C equal to 1, no? Because B is eventually at the end of body number 2, times U of B. Sorry, no? QF. And this is U B. eventually you have that this can be written as 0, 1, 0, 0, 0, 0, because this is xi at point, this is a psi, the shape matrix at xi equal to 1, applied over, you have 3, you have 4, you have 6, is equal to QF 4, 0. Okay. This is instead what? Well, we have already seen this kind of. This is L0, no? The initial position of point B, the undeformed one. So that RB, with no surprise, is what? Is L plus QF4, 0. In fact, if you remember, QF4, as we have seen before, is the axial displacement. In fact, it is along the direction 1. So everything comes back. And so this means that basically our condition becomes as follows. R plus A times RB becomes R1, R2, cosine of theta minus sinus of theta, sinus of theta, cosine of theta, applied over L plus Q4, 0, equal to R1, 4, R2, 4. So my boundary condition equation at B are R1 plus L plus QF4 cosine of theta equal to R14 and R2 plus L plus QF4 and the sinus of theta. Okay. So this basically closes our exercise, our example. So you see, we have gone through all of the elements that we have studied in the theory so far. So the shape matrix, so we have defined the displacement field through the imposition of the physics. We have defined the shape matrix. So we have defined the displacement field. We have defined, in consequence, the matrix of mass, matrix of stiffness, the external forces, and then the boundary conditions. All of it for a simple system. This basically closes this chapter dedicated to the study of the dynamics of deformable bodies. Next chapter will deal with the use of finite element methods, okay, in multi-body systems. So we will see different formulations for the implementation of finite element techniques in the multi-body, in the study of multi-body systems. Eventually, the last part of the course, if we have enough time to do it, will encompass order reduction techniques, like Gaian iron. I think we have already seen some of them, no? We will see them a little bit more into detail. And this was basically will conclude the course. Tomorrow we have the last lecture of the MSc Adams seminar. You will basically finish the exercise on the satellite, and you will be given an assignment. Okay, probably you will be, I don't know, I think you will be divided into groups to be seen. And the idea is that you try to complete the assignment, and you can have, I mean, you have nothing to lose if you don't do it correctly. Meaning that you can have a value going from 0 to 3, and this can spare you a question. But the completion of the assignment is mandatory, so you have to try to do it. Then, if it's not done correctly, you can ask for an additional question. But you have to try to do it, because me and Engineer Catalani, we are working on it. We will correct it, so it's nice for you to, at least to try to do it. Okay. This is all. Okay. So
Prof?
we'll see each other tomorrow.
Prof?
Yes?
Tomorrow, is it online, or is Mr. Catalani going to come to the class, or is it online?
No, as I wrote, it's going to be, unfortunately, again, remote. But for you for those of you who will be willing to stay here, you can follow from class, from here.
Okay.
With the projector and everything.
Okay, thank you.
No problem.